Hello, I'm Dave Ditzel from Sun Microsystems Laboratories, and I'm here today to talk to you about SPARC version 9. And that topic is really about how we went about adding 64-bit addressing and making the SPARC architecture more robust for the future. Let me tell you a little bit about SPARC as background. SPARC is Sun's processor architecture. It stands for a scalable processor architecture, and we introduced it in 1987 in the first Sun 4280 server. At that point, the SPARC architecture, as opposed to the workstation implementation, was called version 7, which shows we'd gone through a number of implementations before we actually released it. It was a classic 1980s style RISC, and we had some very simple goals for it. We wanted a simple but very fast processor to put in our workstations. One of the things that was interesting about SPARC is we made it an open standard and let several companies implement and manufacture chips to the SPARC architecture. The SPARC architecture itself changed very little since its introduction. We've moved from version 7 in the first introduction to version 8 in 1990. And that architecture definition was available in bookstores to what we call the SPARC Architecture Manual. So when we're talking about SPARC version 7, version 8, and version 9, we're really talking about an instruction set architecture. When we moved from version 7 to version 8, we added a couple of new instructions. We added integer multiply and divide as examples. We also added to the architecture manual something called the memory model, which is a definition of how main memory interacts with the processor. And this is particularly important when you're trying to build multiprocessor systems. We added a definition for a reference MMU also, so people doing implementations of the chip would know what kind of standardized MMU would be most appropriate for the Unix operating system. But overall, we made very few changes to the SPARC architecture through its introduction to this point, largely because we were trying to keep stability for the software base. If you change your instruction set architecture with every new chip implementation, it's very difficult for software vendors to port all their applications every time. Well, now it's time to make another larger change to the SPARC architecture, and we'll be talking about that today. When we review the SPARC architecture, it's somewhat of a classic 1980s style of RISC. It had 32-bit fixed length instructions and 32-bit addresses. Operations were done using a 3-address register-to-register style format. There are only about 70 instructions in the initial definition of SPARC. There are two simple addressing modes, register plus register and register plus offset. SPARC uses a delayed branch technique, where a branch is taken, one instruction after the branch is executed, although in SPARC's case, you can also annul or cancel that instruction following the branch in certain cases. SPARC also had a fairly minimal interface between the hardware and the operating system. It was just enough to get Unix up and running and be very inexpensive to implement. In these respects, SPARC is like a lot of the other RISC architectures we've seen originate during the 1980s. One of the differences with SPARC, however, is something called register windows. And this is a way in SPARC where we can use a lot more on-chip registers, in SPARC's case up to 520 integer registers, although most implementations only have about 130 registers on chip. At any one point in time, 32 of those registers are visible to the instruction set. You can move around in what we call a window of this larger register set using save and restore instructions to change which of those registers are visible. One of the benefits we've seen from register windows is being able to make procedure calls very fast. If you want some more background on the SPARC architecture itself, there's an excellent videotape called The Design and Development of SPARC in this series by Wayne Rosing and Dave Patterson. Let me talk about one of my pet peeves first in terms of describing an architecture here, which is that a lot of people confuse the difference between architecture and implementation. An architecture is something that spans over a wide number of implementations. SPARC, in fact, at this point has had over a dozen different implementations, starting off with the initial gate array SPARC chip made by Fujitsu, through various speed enhancements and embedded control chips by Fujitsu. LSI Logic has also made a series of different SPARC chips. There's an ECL, which is another word for bipolar transistor ECL chip made by Bipolar Integrated Technology, which is used by Cray Research in a SPARC supercomputer. More recently, Texas Instruments has introduced the SuperSPARC chip and MicroSPARC chip, and Cypress Semiconductor has introduced the HyperSPARC chip. Now, these implementations have particular characteristics such as clock frequency, cache sizes, performance, but that's not true of an architecture. So today what we're going to be talking about is that instruction set architecture, so we won't be going over any of those particular implementation characteristics. Well, we started with SPARC version 7 and 8, and we've been doing a lot of thinking about what are the long-term needs for processor architectures in the 90s. And we came up with a list of things that were very important when we were considering what to change for SPARC. One of the most important was trying to achieve strict upwards binary compatibility. And the reason for this is most people have a far larger investment in the software they have than they do for the actual hardware workstations or other computers. There was also a clear need for a larger address space. Most RISC computers today have only a 32-bit address space, and in the future, in the next few years in fact, we'll be able to put more physical DRAM into a box than that 32-bit physical address space will provide. We wanted to have better interfaces for the operating system. The style of design of operating systems themselves are changing, and we want to be able to better support those. Multiprocessors are also going to become very prolific in the 1990s, and we wanted better support for multiprocessor systems. We've learned a lot about building multiprocessors through some initial SPARC implementations, and we learned a lot of things that could make those implementations more efficient. We wanted to provide better support for lightweight threads in SPARC and support for object-oriented programming. One of the other issues that hasn't been thought about a lot in the past is better support for reliability of system and fault tolerance. And we had some ideas there we thought we could make some contributions in. We've also learned a lot about compilers since the initial RISC architectures of the 1980s, and we put some changes into SPARC version 9 to help there. Superscalar chips are becoming very common. That is to say, chips that execute more than one instruction per cycle. And with every year going by, it seems like we're executing more instructions at a time. This causes some complications. So we wanted to see if there was something we could do in the architecture to make this type of implementation more efficient. And of course, we're always concerned about performance. And so we looked at what kinds of instructions we might add to the SPARC architecture to make them more efficient or yield higher performance on programs. So the real question we were dealing with here is, how do you go about evolving an already existing architecture? Well, one of the things we did was we thought about it for a long time. In the case of SPARC, we thought about it for about 4 years before we made any actual changes. We had a lot of discussion amongst various members at Sun and in a number of other companies. In fact, the SPARC architecture evolution is not controlled by Sun, but through a group called SPARC International. And it consists of a number of companies, including Sun, Cray Research, Amdahl, Fujitsu, HAL, ICL, Matsushita, LSI Logic, Ross, Texas Instruments, and over 250 other companies. About a dozen of these companies participated in the evolution of the SPARC architecture. One of our goals was to make performance-based changes based upon measurements in the architecture. So we used a lot of benchmarks to try and determine whether a particular instruction set change would in fact yield any practical benefit. And then we rated those and only put in those things that were the most significant in performance. A number of other things you have to add to the architecture are more in the area of feature enhancements. And here sometimes you have to use your judgment. Support for fault tolerance, for example, is not something you can easily go out and measure by running a few benchmarks. One of the problems we had was a set of constraints. We already had an existing instruction set architecture, and there were only so many spare opcodes to use. So we had to work within the constraints of what was available. We had a number of competing proposals for how to extend the address space, for example. One thought was to use a segmented addressing scheme. The Intel x86 architectures, the IBM RS6000, for example, use this type of scheme. Another approach was to completely throw out SPARC and start over with something new. An example of this trend is going from the VAX architecture to the Alpha architecture. One of the things we also wanted to do was to come up with a flat 64-bit address space if possible. So many of these different proposals were under consideration. Well, the biggest decision we made, and the overriding concern really, was how we extended the address space. And it turned out there was a pretty simple solution once VLSI had progressed enough to let us put some more transistors on the chip. What we've done is to extend all of the interregisters to be 64 bits wide instead of 32 bits wide. By just making this one simple change, all ALU operations, therefore, do 64-bit operations. Loads and stores also will automatically do 64-bit addressing If you take the two addressing modes we have, for example, either register plus register or register plus offset, the size of the register is not specifically mentioned in the architecture definition. So whatever the size of the register is what will go out on the address bus. So for example, if we had an instruction that said, load what's pointed to by register 8 plus the value 32, the actual width is not specified in that. So whether we had a 32-bit machine or a 64-bit machine, depending on how wide we made the registers, we would get an address out on the bus of that side. So this one simple extension provides for 64-bit addressing and for 64-bit operations. But it turns out this has far less functionality than we would really like if this were the only change to be made. Another strong consideration for what we wanted to add to SPARC was the compatibility model. It turns out we were able to come up with a very simple rule to provide compatibility. If all of the previously existing instructions were to generate exactly the same results in the low order 32 bits of a register as they did on a 32-bit version 8 SPARC, then all of the old version 8 SPARC programs could be run on a version 9 architecture. Therefore, one of the things we had to do is the fact that the old 32-bit load still had to load only a 32-bit value even though it was loading it into a 64-bit register. The existing branch instructions had to use a 32-bit condition code rather than what you might imagine as having the condition code set off a 64-bit value in a new 64-bit architecture. The other interesting instructions were shifts. And the feature there was that they would not be allowed to have the shift value cross the 32-bit value and shifting down toward the lesser significant bits if we wanted to keep compatibility. So clearly, under these constraints, we have the need for some additional instructions in the architecture. So what did we do? Well, here's a list of some of the new 64-bit instructions we provided. We provided a load extended instruction to load a 64-bit value into a register, and a store extended to store a 64-bit value. The real question is then, what happens with the old 32-bit loads or stores? Do they sign extend, or are they an unsigned load? Well, it turns out it doesn't really matter, but you're going to need one of each kind. So we picked the previously existing 32-bit load to be an unsigned load, and we've added a new instruction for a 32-bit signed load. We've also added a full 64-bit multiply, sign divide, and unsigned divide instructions. And we've also added 64-bit integer to floating point conversion instructions. As I mentioned before, one of the more interesting changes in instructions is with shifts. And let me explain why we needed, in fact, to add 3 new shift instructions. We've added shift right arithmetic, shift right logical, and shift left logical instructions. If we look at this picture, we'll see that in order to do a shift right arithmetic in a 64-bit register, but to still come out with the same result, we need to use a bit from the middle of the register, the 31st bit, in order to generate the right shift, in order to get the same result as we would have had on a 32-bit architecture. So in order to get the operation of a 64-bit shift, we had to go and add a new instruction so we could take the bit at the leftmost part of the register and shift it all the way over to the right. In this way, a new compiler compiling for 64-bit code can generate the 64-bit operation it wants, but the old 32-bit code will still continue to generate the same results for the existing opcode for a 32-bit shift. We made some other changes in the architectural structure of SPARC. The version 8 SPARC had 16 double precision floating point registers. A small number of key benchmarks indicated that 16 registers was really insufficient for double precision operations. So we added 16 more double precision registers, which for the benchmarks we were looking at seemed to provide sufficient number of registers. This also gave us an additional 8 quad precision, that is to say 128-bit floating point registers. The real benefit here is we're going to get increased performance by reducing the amount of memory traffic because we're keeping more values in registers. Well, a real trick here was how do you encode 32 double precision values without being able to add an extra bit of addressing in the fixed format of the instruction? Well, the trick we use here is to notice that we didn't allow odd numbers for double precision adds, for example. And by using those odd values, we can now access double precision floating point registers in the existing 16 registers that we've added. We've changed the condition code structures in version 9 as well. In SPARC version 8, we had one 4-bit integer condition code register, and we had one 2-bit floating point condition code register. Now, for compatibility reasons, we had to keep the 32-bit condition code register, so what we've done is to add a 64-bit condition code register as well. When you do an integer arithmetic operation that sets the condition codes, both the 32 and the 64-bit condition codes will be set. On the floating point side, we've added 3 more floating point condition code registers. One of the reasons for doing this was to allow more parallelism for superscalar chips, where you want to be launching multiple floating point instructions at the same time. The real key here in having multiple condition codes is that we're trying to avoid a single point of serialization in the machine. For example, if we wanted to do several compares simultaneously and only had one condition code, we'd bottleneck for that one resource. By having several condition codes, we can launch several operations in parallel and not be constrained. Branch instructions is something else we thought a lot about, and the reason is simply because branches are a big performance problem for any modern machine. Performance would clearly be higher if we could predict what direction a branch was going to take. So what we've done is to implement a number of new branch instructions, and in each of these instructions we have 1 bit set aside for branch prediction. This 1 bit can be set by the compiler when the program is generated, or set in some other fashion by software. The new branches also allow you to select between a 32 or 64-bit condition codes, or to select one of the new 4 floating point condition code registers. We've also added an entirely new kind of branch. It's called branch on the integer register contents. One of the reasons we added this is we did a lot of measurements of what common pairs of instructions were in SPARC. And by far the most frequent operation was doing a compare and then immediately branching upon that value. To look at these kinds of statistics, you might go to the 1991 ASPLOS proceedings. There's a good comparison of SPARC versus MIPS, and you'll see this result there. By having a single instruction which can test the value of a register and then branch on those contents, we can reduce the overall number of instructions by a fairly significant amount. This avoids having to have a separate test instruction in front of the branch. But another real benefit of this instruction is it gives the effect of having multiple integer condition codes, because we can compute any arbitrary condition and put it into a register, in any of the general registers in fact, and then branch on any of those general registers at a later point in time. So again, here's how we avoid the serialization problem on the inner side of the register set in the same way that we added more floating point condition codes on the floating point side. The problem we had is there was no efficient way to encode multiple integer condition codes on the integer side. And in the end, after thinking about it, we decided that the solution of putting a condition in a general purpose register was a much better solution anyway. We've added a number of new instructions in SPARC version 9 that will let the kind of compilers we expect to construct in the 1990s be able to take more advantage in order to get better levels of performance. Let me give you some examples of these instructions, though not an exhaustive list. One of the instructions we've added is to prefetch data and instructions. The reason we've added this is we have a problem in machines. When you take a cache miss, you can lose a lot of performance. And this is only going to get worse as microprocessors get faster and the speed of main memory stays about the same. So the solution we proposed is to add an explicit instruction under compiler control to let you go out and to prefetch either data or instructions. The benefit here is simply to reduce the amount of memory latency. If we can set a prefetch up far in advance of actually needing to load the value, then we can avoid having multiple levels of cache misses. We've also added support for misaligned data. The basic problem here is that RISC computers tend to require data to be aligned on natural boundaries. For example, a 64-bit piece of data would have to be aligned on a 64-bit boundary. But the Fortran language, for example, allows double precision 64-bit numbers to be put on arbitrary boundaries. The additional problem is that Fortran compilers often can't tell if this data is aligned properly or not, or on a natural boundary. So what RISC compilers have done in the past is to use two 32-bit loads because they could assume that at least a double precision number was aligned on a single precision 32-bit boundary. Having two 32-bit loads is a big performance loss over doing one 64-bit load. Now this is really sad because almost all of the time these double precision 64-bit numbers are in fact aligned on natural 64-bit boundaries. It's only in a rare case are they aligned on some other 32-bit boundary. So what we've done is to provide a fast trap specifically for unaligned access errors. The benefit here is we can let the compilers always use the load double instruction, and in those rare cases where the data is aligned on an odd 32-bit boundary, you can take a fast trap and do a fix-up of this particular code in only a few extra cycles. So this uses the RISC principle of optimizing for the most frequent case and letting software take care of those very rare cases. Something else we provided support for is for non-faulting loads. Sometimes these are called speculative loads. The problem we were trying to address here is that you can't issue a load instruction unless the pointer is already known to be valid. This tremendously complicates and restricts the ability to do code motion in the compiler's scheduler. The solution we've come up with is to allow something called an address space identifier, which is an additional 8 bits which can go with every load instruction to specify a particular behavior that a particular load should not generate a fault. The benefit we get from this is we enable the compiler to schedule loads much further from the use in order to gain performance. Again, we're trying to address the latency issue. Let me give you a simple example written in the C programming language to illustrate how we might take advantage of being able to move the load further away from the use of that data. A very common C program can be seen on your screen, and it simply says, if p is not equal to nil, x gets star p plus y. What we're doing is checking to make sure that that's a valid pointer, and if so, then we can go and dereference that pointer with star p, fetch the value, and use it. If we were to have non-faulting loads in this particular case, we could do the equivalent of going ahead and dereferencing star p here and putting the value in a register, and then letting the compiler later do the check to see if the variable in p was valid address or not, and then if it was, go ahead and do the computation. The point here is that the program will not terminate if p had been an invalid pointer, and that the software can additionally check later on for whatever check it wants to do to see if it believes the pointer was valid. This is one of the largest performance improvements we've made to SPARC in terms of an instruction set change. Some programs, in fact, show up to a factor of 2 performance improvement. It will help a lot in doing things like software pipelining of loops. In version 9, we've added something called conditional move instructions to SPARC. The problem here is a very simple one. Again, we're addressing the branch problem. Any branch instruction will tend to hurt performance in a high-performance microprocessor. The solution here was to introduce a new type of instruction called conditional move. The benefit here is that it can eliminate many different kinds of branches. Let me give you an example of how this would work. Again, if we had a piece of C code that said, if A is equal to B, then D gets 7, else D gets 8. For the old version 8 SPARC code, this might come out of the compiler as a series of 7 instructions where we do a compare, we do a branch around if that value is not the initial tested way. We can assign the value 7 one way, otherwise we branch around and we assign the value of 8. For the new version 9 code, we can take this same C fragment and compile it into only 3 instructions. What we would do would be to subtract A from B to see if the values were equal, and we'd put that condition into a register that I've simply labeled here R test. Then we can use an instruction called move register is 0, where if the test value is true, we'll move 7 into the value RD. And another instruction, move register not 0, using again our test register here to move the value 8 into RD. The new code for version 9 here will only be 3 instructions and will have no branches. In fact, most of the branches that tend to occur in programs are over very short distances, and we expect many of those branches to be able to be replaced by conditional moves. For those of you who are looking for some of the more advanced optimizations you could do with the V9 changes, we have a very special instruction that allows us to do alias correction to help us support much better code scheduling with the compiler. Let's take a look at an example here to see how this would work. We might have a code fragment which came down and wants to store a double precision floating point number in the floating point register 1 into what's pointed at by register 8. So we can do that store. Then we'd want to do a load of a different register, R9, and put that in floating point register 2. Once we've done that load, we want to do a floating point add of register 2, added to floating point register 3, and put the result in floating point register 4. Now, in order to optimize performance here, we would like to move this load as far forward as we can away from the use in the floating point add. Well, in many existing computers, that would be very hard to do because you wouldn't be allowed to move the load up ahead of the store because you couldn't tell if there was an alias problem that perhaps the pointer in R8 was the same as the pointer in R9. But in version 9 code, we can go ahead and do the load long before the store to load the value into floating point register 2. Sometime later, we can come down and do the store. And then what we'll do is to do a check to find out whether register 8 was the same as register 9. So we'll simply subtract those two registers and put the result of that test in some other register I've labeled here rtest. And then we'll use the new version 9 instruction called floating move if register 0. And there's a wide variety of different kinds of conditions one can test for here. So if these two registers were equal according to the value in rtest, we will then move floating point register 1 into floating point register 2 and correct for the fact that that store might have been at the same address as the load address. Finally then, we can do the floating point add knowing that we'll get the correct data here. This turns out to be a particularly important optimization as we're going towards future superscalar processors doing many instructions in parallel, and where it's going to become critically important to move these load instructions back as far as we can. Superscalar pipelines are going to be executing more and more instructions every year as we learn how to build higher performance superscalar machines. The SPARC version 8 instruction set already does support the ability to implement superscalar processors through having simple to decode instructions and having separate integer and floating point units, amongst other features. We've seen examples of existing superscalar processors with the ROS technology HyperSPARC processor, which does 2 instructions at a time, or the Texas Instruments SuperSPARC processor, which does up to 3 instructions at a time. There's still many improvements to make in terms of superscalar design, and from these early implementations, we've learned a lot about what we wished we would have had in SPARC at this point. And now with SPARC version 9, we're able to make some of these changes. Let me tell you what those are. To enhance superscalar operation, we've increased the number of floating point registers. This will let us have more floating point operations active at any one point in time. We've introduced the notion of speculative loads so we can do things we would have been constrained from doing at an earlier point in time. We've introduced the notion of multiple condition codes both in the floating point unit and in the integer unit to avoid serialization problems. We've added branch prediction to processors in order to make branches go away. We've added conditional move instructions to try and make branches go away. Again, you can see branches are a big factor for superscalar designs. And we've added something called a memory barrier, which will let us do synchronization better for large-scale multiprocessor systems. Every one of these items, in one way or another, is promoting the use of parallelism. And superscalar designs really are all about trying to achieve more parallelism on the chip at the same time. Well, one of the things we've done in version 9 is to completely redesign the operating system interface for SPARC. There are new privilege registers and new privilege structure in SPARC version 9. We have completely removed the processor status register. In the previous version 8 SPARC, we had one 32-bit register into which we had crammed a whole bunch of 3, 4, and 5-bit fields. Now what we've done is broken these out each into separate registers of their own. This provides quick and clean access to resources when you take an interrupt or trap, want to quickly read something and get back. There's no need to spend a lot of time packing and unpacking some processor status word. We've provided new privileged instructions. I won't go into a lot of detail right now on these, but these provide support for the new trap structure, ability to manage the register windows in a very different way, and provide access to other privileged resources in the machine. The good part about all these changes we've made in the operating system interface is these were all privileged instructions we were changing, and the user-level application programs remain completely unaffected by these changes. Let me talk about some particular ways we've tried to support operating systems in version 9. One of the things we wanted to do is to support the microkernel style approach to operating systems better. One example of how we're doing this is through the introduction of stack traps. This allows us to layer the software. For example, the principle of a microkernel is that you can layer software in various regions, and we don't have to worry about taking traps from one particular region into another. That's now allowed. We provided support for lightweight threads. The way we've done this is provide very fast user-level thread switching. This is done primarily through the new register window structure. We've provided for much faster context switching. We've done this both through the ability to do banking in the integer registers and providing dirty bits on the floating point register set. And we provided more support for object-oriented systems. One of the ways in which we've done this is to provide support for cross-address space calls more efficiently. We have also tried to provide support for very large-scale multiprocessors where you might want hundreds or thousands of processors working together. And one of the things we have done is to define an additional relaxed memory order memory model. This again defines exactly how main memory works when a large number of processors are involved. When you have a large number of processors, the transactions going on the bus to main memory with multiple levels of caches and store buffers can become very confusing, and it's imperative that one rigorously defines exactly what happens if one is to be able to program at all on these multiprocessor systems. To go along with this new relaxed memory order, we've added a new memory barrier instruction. This instruction will provide an explicit synchronization point for very weakly ordered memory systems. We've also made some changes to SPARC version 9 to support reliability and fault tolerance. One of the instructions we've added to SPARC is called compare and swap. This is actually a fairly well-known instruction for which there exists some very good research papers in their literature. Maurice Herlihy has a very good paper showing how one can use compare and swap. It's a very efficient multiprocessor synchronization primitive. But in addition, this particular instruction has some fault-tolerant features, such that if the machine was to crash, and in fact even be in the middle of this particular MP synchronization instruction, you can tell exactly what happened because of the atomicity of the operations and find out which processor failed. We've added multiple levels of stack traps. The benefit of stack traps for more reliability is it allows us to more gracefully recover from faults, as well as to provide greater efficiency in the operating system. SPARC version 8, by contrast, had only one level of trap. When you trapped into the kernel, you had to take a lot of care to make sure that nothing you did could possibly cause another trap to occur, or that would have been a fatal error in the machine. If we looked at SPARC version 9's multiple levels of stack traps, I can give you an example of how these might typically be used. For example, at level 0, you might be running a normal user program. For whatever reason, you might take a trap, and you come into the kernel at level 1. This might be, for example, to do a system call, to have an interrupt handler, or for example, to do fast instruction emulation. You can then operate at this level and return to level 0 fairly quickly without having to do a lot of checks. But while you're in that level 1, you might get another kind of exception in the operating system, and you can trap to level 2, where another OS handler can deal with it. In that level, you might, for example, get a page fault in the operating system. If so, you can then trap to level 3. Level 3 is normally as far as you would expect to go in terms of taking a normal trap. But if something catastrophic happens at that point, you can go to level 4 for what we call our red mode handler. Red mode is what we call our reset, error, and debug mode. And we have defined in the architecture of version 9 a very specific set of standards for how you can recover from particular kinds of errors when you go into this level of trap. This should let us build very robust and fault-tolerant systems and have the hardware actually be helping us out here rather than getting in our way. We provided for fast traps and context switching in version 9. We've redone the trap model from version 8 such that we can get to specific trap handling code much more quickly. One of the examples I showed you before was the unaligned trap error. There are a number of other specific trap types we can come into in only a few cycles, execute just a couple of instructions, and get back to user code. We've also provided 8 new registers that we call alternate globals, So when you come in and take a trap, you have 8 fresh registers in the kernel for scratch registers, so you don't have to save away registers before you do a computation. Quite often when you're taking a trap, you only need to execute a few instructions, and we had as much overhead previously in saving away and restoring registers as we actually did in servicing the interrupt request. In this way, we don't have that additional overhead to deal with. The real benefit here is very fast system response, fast instruction emulation, and getting in and out of the system very quickly. We've added multiple levels of stacked traps, and let me explain again why this is particularly important. Because this would allow a trap routine itself to allow another trap to happen. When we were examining the Unix operating system, one of the things we found is we were spending a lot of time in the trap handlers just checking for some very obscure condition that would likely never happen because we couldn't afford to let another trap happen while we were in the trap handler. And one example of this would be the register window handler that went from almost 100 instructions in version 8 SPARC down to only 19 instructions in version 9 because we could avoid a lot of this excessive checking. An error can still occur, but then you'll trap to a different routine which can handle the abnormal condition and recurred. Almost all the time, in fact, these abnormal conditions will not occur. So again, we're taking advantage of the RISC paradigm of supporting the most common condition very, very quickly and allowing abnormal conditions to be handled in software. The real benefit to us is going to be overall performance gains and a much cleaner programming model as well. I mentioned before that we need to do fewer saves of registers during context switches. Let me explain how this works a bit more. In the floating point register set, we've added 3 new bits to the system architecture. One simply enables or disables the floating point unit completely. Many integer programs never use the floating point registers, so on a context switch we can completely avoid the need to save or restore these registers. If you're doing context switches very frequently, even in a floating point program, you may not touch all of the registers. And we've taken the floating point register set and divided it into 2 halves and provided a dirty bit for each half. If you write into one of those halves of those registers during the course since the last context switch, that bit will be set. If you have not touched any of those registers, the bits will not be set, and therefore when the operating system gets called, it can quickly check these bits and determine that it does not need to save away the floating point registers, thereby by saving time on a context switch. We've done something for the integer registers as well, which is to change the register window model. And what we expect people to do in the future is to use the large number of registers in SPARC on the integer side for doing bank switching between different processes. One process can be running with one set of registers. You do a context switch, you may come find you don't have to take any change to the floating point registers, and you'll simply switch to a different set of the integer registers. Therefore, you won't have to save any registers away between a lot of different context switches. The overall benefit, of course, is very fast context switching when you don't have to save any registers away. We think this is more efficient than any of the other architectures we've seen. Well, we've been talking a lot about what things we added to SPARC. I think it's only appropriate to talk a little bit about what things we left out of the architecture. Well, we were thinking about this for 4 years, and we had quite a list of things people wanted to include. I think we probably added less than 10% of those requests. Just a couple quick examples. We added no decimal or string instructions. All the studies we did showed that they really wouldn't add much value. We were very tempted to one point to add what's called the drystone instruction, which searches for a 0 byte and tends to speed up the drystone benchmark a lot. But again, we were trying not to make changes to the instruction set architecture just because of a particular benchmark. One of the questions you might have is, well, how do you load a 64-bit constant? Maybe we need a new instruction for loading that. To load a 32-bit constant in SPARC, you do it in 2 instructions, where you load a low piece, and then there's another instruction called set high, which loads the upper bits of a register. Clearly, if your instruction is only 32 bits long, you can't put a 64-bit constant in there with that instruction. So there were some proposals to have, in addition to set high, a set mid, and a set very high instruction. Well, we found out in studying it there were a lot of common instruction sequences that would let us generate 64-bit constants very efficiently, or also to simply use a load instruction to load them from a constant table in memory very quickly. We didn't add a multiply add instruction, and we had a lot of discussion on this topic. We didn't like the fused mul-add type used on the IBM RS6000. One of the reasons being that when you do a mul-add, you get a different result from doing a multiply followed by an add, because you only get one rounding instead of two. And in doing this, you lengthen the floating point pipeline, and lengthening the pipeline is typically never a good thing to do in a machine. By having superscalar execution, we found we could launch a multiply and an add at the same time to get the same or sometimes better performance than a single mul add instruction would have had, because we can schedule the multiply and the add separately and have a lot more compiler control over what's going on. One of the things we left out of version 9 were a lot of the version 8 privileged instructions. Again, I mentioned we redid the privileged architecture of version 9, and so a lot of those instructions no longer exist. On the user side of the instructions, we need to keep all those instructions there for compatibility, although it's not clear exactly how we are going to provide those in each and every implementation. Initially, I suspect we'll provide compatibility by doing hardware implementations of these instructions, but in the future we may implement these instructions in software. And so we have noted a number of version 9 instructions in being of the category of deprecated instructions. And for these instructions, it's suggested that you try and avoid using these so that in a few years these instructions will tend to disappear from the binaries of programs. One example of a deprecated instruction are the 32-bit multiplies. The 64-bit multiplies completely supersede these instructions, and there's really no need for the old 32-bit multiplies. Let me just make a couple of comparisons between SPARC version 9 and some other architectures. One new 64-bit architecture is the DEC Alpha. Its principal characteristic is that it's not an evolutionary architecture, but it's a completely new architecture. If I were to compare the style of Alpha, in my opinion, it's really very much like the classic 1980s style of RISC instruction set architectures. In fact, it's a very minimalistic style of architecture, and in fact I think they had their own reasons for doing that, but it provides some restrictions as well. For example, when you want to store a byte into memory, it may take up to 5 instructions to store that byte. And it has no compatibility with previous implementations from Digital Equipment Corporation. If we look at the MIPS R4000, it was an evolution of an architecture, but what they did in doing that evolution is to essentially only add 64-bit extensions. All the other kinds of things that we have done to SPARC in addition to 64 bits were not done in that particular architecture. If you look at the IBM RS6000, it used a segmented addressing scheme to get more than 32 bits of addressing. More recently, the RS6000 architecture has evolved into the PowerPC architecture, where they have moved to a linear flat address space as being possible, and that has many similarities to what we have done in SPARC version 9. The HP Precision architecture is still a 32-bit architecture, using a segmented scheme to get larger than 32-bit addresses. And of course, perhaps the most pervasive microprocessor architecture is that of the Intel x86 family. One of the common questions I'm asked is, will CISC catch up? And I guess my comment on that is that the instruction set architecture there has a small number of registers and really shows a lot of the heritage from its 8-bit design. So I think what's happening is that the implementations are borrowing from a lot of the techniques that RISC computers use, but it's going to be impossible for that series and the family to borrow from the architecture of the RISC instruction sets. So because of that, I think it's very unlikely that that architecture in the long run will ever catch up to where the RISC architectures are. In summary, SPARC version 9, I think, is really an excellent case study of how computer instruction sets can evolve. What we've achieved with version 9 is to be able to extend SPARC to provide a full, flat 64-bit address space. But in addition to that, we've done a number of other things to support more robustness in the architecture so it will survive over the next decade or two. We provided support for fault tolerance, faster context switching, support for new kinds of compiler optimizations, support for more efficient superscalar implementations, and a clean structure for more modern operating systems. We've been happy that we've been able to do this and also provide 100% upwards binary compatibility with our previous version 8 architecture. When we look to version 9 implementations of this instruction set architecture, I certainly expect to see them within the next year or two, and they will provide a much larger virtual address space as well as physical address space, provide superior performance to what we've had in version 8, to provide much more robust systems than we've had in the past, and hopefully be more cost efficient at the same time. Now, unfortunately, I've only been able to go into a small number of the many detailed changes we made in SPARC version 9. What I would suggest you do for further details is to get a copy of the SPARC version 9 instruction set manual. This should be available in bookstores in 1993, or before then, you can call SPARC International directly, and they're located in Menlo Park, California. You'll find them with the phone directory system. So I want to say thank you very much for listening to what we've done with SPARC today, and I hope it's helped you understand how we take an architecture and can evolve it for the future.